In this section, we're going to be looking at frictional forces. We're going to look at two kinds, static and kinetic. So first of all, a frictional force is going to be a force that's parallel to the surface of the object. So you can see two different situations in these pictures. So the first one, you have an object that is on a flat surface. So the friction force, you can see how it's parallel to the surface that object is on. So we would have an applied force, maybe somebody's pulling a rope, or maybe they're pushing the box. Friction will be opposite the applied force, or opposite the way the object's moving. Down below, we have a ramp. If the box is sliding down the ramp, then friction is going to be up the ramp. And again, it's parallel to that surface. If the box were being pulled up the ramp, then the friction would be going downward. Here we're going to look at static friction. So static friction is the frictional force that keeps something from moving. So here you can see the guy's pushing on the box, and the surface of the box that's in contact with the ground, there is friction that's keeping that box from moving, and that's the static friction. So this is going to depend on the area of the surfaces that are touching. It's going to depend on the types of the surfaces. So obviously, if you have a gravel road versus an icy pond, the gravel road is going to be harder to get something started moving versus on an icy pond. Here we're going to look at the friction equation. So here you see the force of friction equals, and this is the symbol mu, but it's the coefficient of friction. So this is dependent upon what the surfaces are that are in contact. This is going to be a ratio, so it'll be point something for your number. And then this is our normal force. So if you remember, and we go back and look, weight is downward, and then the normal force is the force that opposes the weight. So to find the force of friction, you're going to take your coefficient of friction times your normal force. So here we're going to look at a problem. So we've got a skier that's standing motionless on a horizontal patch of snow. They have a tow rope that's pulling them forward. The skier's mass is 59 kilograms, so that's going to be downward. And it tells us the coefficient of static friction is between the skis and the snow is 0.14. We want to know what's the force that the tow rope can apply to the skier without causing her to move. So what that means is if the applied force is greater than the friction force, then the object's going to move. So as long as the applied force is the same as friction, the person's not going to move. So we need to find basically what is the friction force, and so our applied force would have to be anything larger than that to get the skier to move. So the first thing we're going to need to do is figure out her weight. So if I've got a 59 kilogram is my mass, then the skier's weight is going to be 59 times 9.8. So her weight is going to be 578.2 newtons. Now I need to define the weight because if the weight is downward, then my normal force is the same as the weight, only up. So 578.2. My friction force, and we're going to use big F sub little f to mean friction force, equals coefficient times my normal force. They tell us that the coefficient is 0.14 we just determined that my normal force is 578.2. So my friction force turns out to be 80.95 newtons. And so if we go back to the problem says, we want to know what's the magnitude of the force that the tow rope can apply to the skier without causing her to move. So if we apply more than 80.95 newtons, then the skier is going to move. So our answer is the 80.95. The next type of friction is kinetic friction. And kinetic friction is the friction that an object has once it's already moving. So this is going to be more like getting it to slow down. So static is trying to get the object to move. Kinetic friction is once it's moving, it typically slows the object down. Same equation. So kinetic friction equals coefficient of kinetic times your normal force. There will be a lot of times that we'll be working with friction problems on angles or on ramps. And so we're going to look at some of the situations that you're going to have to consider. Now, I will say that you will have to evaluate each problem to determine which way the object's moving, if there's an applied force, all kinds of different things. So you won't be able to just say, here's the formula for friction problems on a ramp. You're going to have to evaluate what's going on before you start the problem. So first of all, one thing I want to talk about is weight. You'll usually be given the mass and then have to find the weight. So mass times 9.8. If we look here, they show us mg is pointed down, perpendicular to the actual ground or the earth. Weight is perpendicular to the earth, not the ground or the hills that might be on the earth. So if we have this box sitting on a hill, the weight is still going to be perpendicular straight down to the earth. So that adds a little complication to our problems. So they will be telling you what the angle of the hill or the ramp might be. And so it's designated here by this angle symbol. But one thing you'll need to realize that whatever the angle is of the hill, maybe this is a 40-degree angle. Then the angle that the weight makes is also going to be that same angle. So if this is 40 degrees, then this angle is also going to be 40 degrees. And so that's going to help you solve this triangle out. So if the object's, let's say, sliding down the hill, if this is the weight of the object here, part of the weight is going to be pulling that object down the hill, and then part of the weight it's also going to be perpendicular to the hill itself. So we're going to have x and y components of weight. So the x component of the weight, and that's an x there, is going to always pull the object down the hill. The y component of the weight is actually going to be the same as our normal force here. Or they've designated it as just the m. So equal to the y component of the weight. And so you'll have to solve out this triangle every time you do one of these ramp or hill problems. So to find the x component, right here, you would be doing weight sine of your angle. And then up here, this would be weight cosine of your angle. And so you may want to jot that down just to remind yourself of that for later problems. I'm going to erase some of this. Now, we've got net force y, net force x. the object's never really going to be moving up or down in that, we'll call it y direction. So that's why we said that the normal force we can say is equal to the y component of the weight. And so those should equal 0. So that's why we can say those are equal. But the x component of the weight, or sliding up and down the hill, we can have lots of different things going on. So first of all, we know that the x component of the weight is always going to be down the hill. Then we'll have to look at what's going on in the problem. Is the box just sitting there on the hill and that weight component causes it to slide down? If that's the case, then the friction force would be up. So then we could say our net force in the x direction, or we can just say net force at this point because we know there's no net force in the y direction, is going to be my friction force is upward and my x component of my weight is downward. So then using that, once I figure out that value, the net force equals ma, so I could solve for acceleration. Or maybe the problem gives me something where I have to solve for acceleration and then find maybe the friction force. Another scenario that might happen, what if they tell us that, hey, we have a force applied upward. And maybe there's a rope pulling that box upward. Well, if the box is being pulled upward, that means the friction force is now downward. So our net force now is going to be applied force is up, and then our friction force is down, and the x component of the weight is downward. So from there, we could solve for the net force. So you really have to set up these problems, draw them out, and see which way the box is moving, what forces are being applied to determine what your net force would be. So let's look at a problem. We've got a box on a ramp with a 30-degree angle. You're pulling a box of books up the hill with a force of 90 newtons. So that tells us our applied force is 90. It tells us the box has a mass of 10 kilograms. So we'll jot that down. Mass is 10. So from there, we can solve for weight. So 10 times 9.8 gives me a mass of 98. So one of the first things that I want to do is go ahead and solve out my weight, x and y. So my triangle, this would be my weight, then my weight x, and my weight y. And so if my angle is 30, that means that this angle here is also 30. So I can say that weight x component is going to be, my weight was 98 sine of 30. And so that gives me 49. And then my weight y component is going to be 98 cosine 30. And for that, I get 84.9. And I'm doing a little rounding here, so as long as you're close. Once I have found my weight y, that tells me my normal force. So that's 84.9. we want to know, let's see, it tells us the coefficient of friction. And so remember, that's a funny looking U. It's called mu, and it tells us it's 0.5. And there's no unit for that because it's a ratio. Find the acceleration of the box. If you remember, anytime you see acceleration, that tells us we have to use net force. We know that the mass is 10. We need to solve for the net force. So if we look at our problem, our net force, so far, we know that 90 is going up the hill. The x component of the weight is going down the hill. And we've got one more force. If the applied force is up, the friction force is down. So we need to solve for the friction force. Friction force, I'm running out of room here, is mu times normal. So we've got 0.5 times 84.9. So my friction force, let's see what I have here, is 42.45. So now we've got our three forces. So we've got 90 up for our applied force. Downward, and we're going to subtract because it's in the opposite direction, our friction force, and we just said that's 42.45. And then subtract our WX, which we said was 49. And that gives me a net force of negative 0.145 newtons. That's my net force. Because it's negative, that tells us something that we probably weren't expecting. If they're pulling up with 90 newtons, but the net force is negative, that means that their upward pull still wasn't enough to make the box go up. It's still going down the hill. So now we know net force is negative 1.45. Our mass was 10, and we're looking for acceleration. So acceleration we find is negative 0.145 meters per second squared. And that's what we were looking for. It's a lot for one problem. Let's do another one. This one's a little bit easier because we are not on a ramp. So we have a hockey puck given an initial speed of 20 meters per second. When you hear initial speed, that's going to tell you, oh my gosh, I'm going to have to find acceleration. So we've got a hockey puck, initial speed of 20 meters per second on a frozen pond. Puck remains on the ice and slides 120 meters before coming to rest. Determine the coefficient of friction between the puck and the ice. So let's draw it out first. There's our hockey puck. We know that it is 2 kilograms. If I have my mass, I can find my weight. So my weight for my hockey puck, 2 times 9.8 gives me 19.6 newtons. Once I have my weight, I can have my normal force, which is 19.6 newtons. They also tell us our initial speed, VI is 20. Puck remains on the ice and slides 120 meters, so distance is 120 before coming to rest. So VF equals 0. And if we have any of those, we know we're looking for A. So we'll go ahead and solve for A because we know we're going to have to get there. We're going to use VF squared equals VI squared plus 2AD. And once we solve for A, That's going to give us an acceleration of 1.67 meters per second squared. We're looking for coefficient of friction. That is in the friction force equation. So if I read this problem, the puck is sliding and it's coming to rest. So if it's sliding, let's say it's sliding this way, and then there's going to be friction backwards. But there's nothing causing it to go forward. There's no applied force. So at this point, if that's the friction force is my only force in the horizontal direction, that's also going to be my net force. So let's go ahead and solve for friction force. Friction force is mu, which is what we're looking for, times 19.6. We know it's the same as the net force. Net force is ma. We said mass is 2, and we just solved A to be 1.67. So if the net force of 2 times 1.67 is equal to mu times 19.6, we can solve for mu. So 2 times 1.67 divided by 19.6, and the mu turns out to be 0.17. Here we have another ramp problem. We've got 20 kilogram box. And the angle of the ramp is 30 degrees. It tells us mass of 20. So we can get our weight by 20 times 9.8. So we're going to put that right here, 196 newtons. So we're going to solve for our weight components of x and y. Remember, our angle up here is 30. So Wx, 196 sine of 30 gives me 98. And 196 cosine 30 gives me 169.7. So that also means my normal force is 169.7. We're looking for the coefficient of friction. So ultimately, we're going to need to solve for the friction force. It says it's sliding down the ramp. So if the box is sliding down the ramp, it doesn't tell us if there's any push or there's any pulls. So this is the force that's causing it to slide down, which means friction will be up because it's going to oppose the way the object's moving. So friction is coefficient times the 169.7 that we found. They have given us acceleration. So that tells us net force equals ma. So m is 20, a is 1.2. So my net force is 24. So if my net force is 24, that's coming from the friction force which we know is, here, we'll do it this way, sorry. Friction force is up minus the weight X component, which is 98. So my net force friction force is going to be 24 plus the 98, or 122, and that equals mu, where did my number go? Oh, sorry, 196. 169, gosh. 169.7, my normal force. So I'm going to do 122 divided by 169.7, and then my coefficient turns out to be 0.72. In this last problem, now we have a ramp of 40 degrees. So we have 40-degree ramp, 3 kilogram block. So we've got 3 kilograms. Then my weight is going to be 3 times 9.8, or 29.4 newtons. So then I go ahead and solve. 29.4, weight in the X, weight in the Y, this is 40. So 29.4 sine of 40 gives me 18.9. And then 29.4 cosine 40 gives me 22.5. So that means normal is 22.5. Some other things that it tells us, it starts from rest. So VI is 0. At the top of the hill, slides down a distance of 2 meters in a time of 1.5 seconds. Find the coefficient of friction. This information here tells me I need to solve for acceleration. So to solve for acceleration, I'm going to use the equation that is d equals 1/2 at squared. And if I plug this information in, my acceleration turns out to be 1.7. I'm going to erase this just to give me some space here. So reading this problem, it's just sliding down the hill. There's no other applied forces. So we've got our Wx down. So that means our friction force will be up. So my net force, we know that net force is Ma. We know that M is 3, A is 1.7. So my net force is 5.1. Now, if our net force is 5.1, we are looking at the fact that if the object is moving down the hill, that means my Wx must be bigger than my net force. So the 5.1 is going to be 18.9 minus the friction force. So then that tells me that my friction force ends up being 13.8. And so that is coefficient times the normal force, which we said was 22.5. So our coefficient turns out to be 0.61.